Previously, we've been looking at functions that were linear growth, that is, they were increasing or decreasing by the same amount each time period, or we've been looking at geometric growth and decay where things were increasing or decreasing by the same percentage amount for each time period. There are many situations where recurrence equations do not represent linear growth and decay or geometric growth and decay. They may be a combination of the two. So we're now going to be looking at situations where we can have a combination of geometric growth and decay with arithmetic growth and decay. The recurrence equation that we have written down says V0 equals the initial or starting position. Previously, we've been having that as the principal, but not all situations deal with money. For instance, you could be looking at an animal population where V0 is the number of animals that we start off with. We're then told Vn plus 1 is equal to R times Vn plus or minus D, so plus D, or Vn plus 1 equals R times Vn minus D. These are two different situations. Firstly, if we look at the formula Vn plus 1 equals R times Vn plus D. R is what we were using for our geometric growth factor. So we know if R was equal to 1, multiplying anything by 1 doesn't change it. But if R was bigger than 1, we know that that is increasing a value when we multiply by a number bigger than 1. If we were multiplying by a number which was less than 1, such as 0.5, then we are decreasing the value when we multiply Vn by that number. We're halving it. But there's a second component there, the plus D. This is where we're adding a number on. So for instance, if we multiply a number by R that is bigger than 1, and then we add another value to it, multiplying by a number bigger than 1 increases, adding another value to it increases further. That means Vn plus 1 is going to be getting bigger and bigger and bigger. If the number for R though was less than 1, so let's say it was a half, we halve our value for Vn. Now depending on what size number we add to it, it's either going to increase or decrease. So there's going to be an interplay between those numbers. Similarly, with the second version of the formula, Vn plus 1 equals R times Vn minus D. R can be bigger than 1 or less than 1. Minus D, we're taking a constant value off. So if we just consider some brief examples. If I make up a question which said Vn plus 1 equals 2 times Vn minus 3. If I said V0 was equal to 2, that would tell me I start off with V0 equals 2, then V1 using our formula would be 2 times V0 minus 3. That is 2 times V0, which was 2, minus 3. 2 times 2 is 4. 4 minus 3 is 1. V2 would be 2 times V1 minus 3. 2 times V2, in this case, is going to be 2 times V1. V1 was 1. 2 times 1 minus 3. 2 times 1 is 2. So we've got 2 minus 3. 2 minus 3 is negative 1. If we go to work out V3, 2 times V2 minus 3. 2 times V2 is negative 1 minus 3. 2 times negative 1 is negative 2. So we've got negative 2 minus 3. Negative 2 minus 3 is negative 5. So you can see that we've gone 2, 1, negative 1, negative 5. We have been decreasing in value. If though, I said this time, instead of V0 being 2, I'm going to say we've got the same equation, Vn plus 1 equals 2 times Vn minus 3, but we're going to have a different starting value. We're going to have a starting value of 4. That means V0 is 4, V1 will be 2 times V0 minus 3. 2 times 4, which was our value for V0, minus 3. 2 times 4 is 8, 8 minus 3 is 5. You can see we've increased from 4 to 5. If I went to work out V2, I get 2 times V1 minus 3. 2 times V1, V1 was 5, minus 3. 2 times 5 is 10, 10 minus 3 is 7. Lastly, I'm going to work out V3. V3, 2 times V2 minus 3. 2 times V2 was 7 minus 3. 2 times 7 is 14. 14 minus 3 is 11. So you can see we've gone 4, 5, 7, and 11.